Okay, so I'm trying to go quickly here. So, this is a work about extracting the higher order logic formulas from English sentence. So the motivations, well, this work on this tentative of having a logical representation of sentence goes back to the 70s or even before, and we have nowadays many different meaning representation approach. And the difference between them are a lot of difference. We could spend much time talking about this, right? Specificity, modularity, robustness, efficient, and so on. Of course, when we talk about semantics of language, we can go over a completely different spectrum and go to approach like natural logic that tries to reason directly with the language, natural language itself. And somehow LLMs are kind of connected to that, right? The idea of trying to extract the a vector representation directly from the text, so avoiding these semantic representation structures at all. But the work that I represent here is based on tools and techniques developed by the DELPH-IN project, and this is a consortium with many different research sites that works with deep linguistic representation of human language. Somehow they are already using these nowadays very common name called neurosymbolic, right? But these consortium is exploring that for a while, right? The idea of how to combine deep semantic and symbolic representation with statistical methods for extracted semantics of text. And the main two pieces of theory that they use are the HPSG for represent grammars and the MRS as a representational language for the semantics. From when you think about these two frameworks, we may have two different perspectives. From the computational linguist perspective, we have questions about what's the proper way to represent different constructions of language, right? And from the semantic perspective, we also have many questions about, for example, how to represent one particular phenomenon, like, for example, the adjective only, right? What would be the best semantics for that kind of adjective? From the NLP applications, then, more practical point of view, we have threads of work about first how to produce good semantic representation that can be useful for different applications and domains. Or we also have questions about, okay, what is this usability, right? What is a good representation and why is it good for a particular application? What are the kind of killer applications that can use semantic representations? Okay, let's put an example to be concrete. So suppose that I have a sentence like this: the oil company ensures no change of poison in the river, right? The MRS is what I'm showing here, right? So this is a very detailed linguistic motivated representation. We see that we have the core of the representation is a bag of predicates, and the predicates capture the predicate argument structure of the sentence. The predicates have these labels on the left that can encode a kind of a tree-like structure of these predicates. We have also variables associated, properties associated to variables. So, for example, if we take X19, we know that it is a third person plural. And we also have in the end of the representation the constraints. And these constraints are a way to encode multiple different possible scope of quantifiers into a single unit representation. And keep in mind that these MRS is one among 13 possible MRSs for that sentence. That means that we have 13 different possible readings for this sentence according to the HPSG grammar. And I'm showing here just the first one. Okay, so another way to see these MRS is like this. This is what we call the dominance graph. So basically, what we're showing here is that the quantifiers force some scopes of the variables, and some of those arrows, the red arrows, indicate that those are unconstrained. So it means that there are many different possible ways to transform this graph into a single tree. And so that is a kind of combinatorial explosion way to deal with the ambiguity, right? Because this simple sentence has 13 different readings, and for each reading we have one dominance graph that could be expanded in many different possible trees depending on the order that I choose to attach the quantifiers. So for example, if you take here label H8, then this means that it can be attached in two different points of a single tree. Okay, and what we want in the end of the day, what we want is to have some concrete logical language to work with, right? And that would be one possible formulas that we want to obtain. And once we have a concrete language, then we can use some kind of a prover, right? A theorem prover, automated theorem prover, or even ITP to reason over that formulas, right? And what I'm showing here is that for this single MRS that I showed previously have at least two different formulas depending on the order of the quantifiers. And you can see here that the order basically differ in a way of how the negation could outscope or not the other quantifiers. So when we think about this idea of taking the MRS from the DELPH-IN communities and try to transform into logical formulas, the interesting thing is that over the last years, we didn't have much work on that. We have very few works that explore the idea. We don't have even a complete transformation from MRS to first order logic. And there is a initial implementation presented in these grammar developed environments called LKB, but not finished. There is also a paper about glue semantics for HPSG, but not developed further. It's just one single paper. And even in the paper that introduced MRS, the original paper from Enkopstake and then Flinch and Pollard and Sag, they have a footnote that's basically saying that, okay, it should be possible to deal with having providing some kind of a direct semantic in MRS or model direct semantic for MRS, but that wasn't never developed. Enkopstake recently also makes some points about the difficulty of going from the MRS to any more concrete logical language. And we all know that, right? So first of all, first order logic looks like not sufficient to arbitrary sentence. And actually the problem is that although we have many proposals of logicals for capture some phenomena of natural language, we yet do not see any unified way to deal with all the phenomena together in a consistent way. We also know that the feasible reasoning is important to do with language, and this is something that we have in our radar for future work. Currently, we try to see applications that could be simple enough to explore the framework and try to increase in complexity. So, for example, one of the applications that we are using this tool is to for example, try to avoid hallucinations of large language models. So in a question answer application, for example, we take a question, we use a large language model to produce a Sparkle query, and then we kind of check if that Sparkle query is consistent with the semantic that we obtain from the sentence. So it's a kind of a double check of what the LLM produces. In the future, we want to explore dependent type. There are many reasons to that. There are some previous work on that. Motivations goes back to this thesis from Arne Hunter on why this dependent type could be a more expressive and adequate language to deal with semantics of natural language. We also this is kind of related with the problems that we have in the first order logic, but also the lessons that we learn from the applying of types in the discipline of types in computer science. So our future plans involve the implementation of everything that we're doing in the linter improver. Is a new ITP that's have been heavily used by the math community. But for now, the things that were presented here is based on the Python implementation of two libraries, ULKB and MRS logic. Now, ULKB is an implementation in Python of high order logic or simple type theory. So it's basically not only the implementation of language, but also some capabilities to federate of multiple different triple stores and knowledge graphs. It's basically, as I said, in high order logic, so it has types, booleans, functions, and quantifying over arbitrary types, and high order function predicates. So the language, I'm not going to detail, but the language of high order logic is basically this one I'm presenting here, and meaning that we don't have, as in first order logic, the distinction between terminals and expression. This is the main difference for people that's more familiar with first order logic. In the MRS logic is the second library. So the idea is that the MRS logic, you use your LKB to represent the formulas. Your LKB is just the language to express the formulas, and MRS logic is the library that translates MRS into the ULKB language. So it's also a Python library. Why we started from Python, because we could reuse some other libraries. So PyDelph-In is a library implemented by the DELPH-IN Consortium to kind of orchestrate the calling of different tools. We're also using UKB, U2 to deal with the quantifiers, the scope resolution of the quantifiers, and also UKB to deal with word sense ambiguation. And OLKB can talk, once we have the OLKB formula, OLKB is also able to talk with provers like e-provers and vampires, Z-trees, and many different provers. And also it's able to serialize to different formats. So the formulas could be serialized to different formats. So what exactly is the MRS logic? So is a pipeline of steps, right? So it has to get the MRS and then do the scope resolution, then convert to simple type or higher order logic. And for that, it had to deal with different phenomena of language, generalized quantifiers, logical and natural language connectives, the variables of events, and the uninstantiated arguments, special predicates, and so on. And finally, at the end of the step, we didn't explore that in this work, but we can also do the word sense ambiguation, again, calling a UKB implementation. So it's implementation of word sense ambiguation. So scope resolution transformed the graph that I presented before, the dominance graph, into a tree. So this is one possible tree, and this is the first step to start the translation. Once we have this tree, what we do is basically go top down in the tree, converting in a compositional fashion. We are converting each node of the tree into a formula, and we end up with a final formula. So this is a sequence of equations that show the transformation of this tree into a final formula. The final formula is one of those that I presented before. So going quickly on the steps of this transformation, the main point, of course, is to deal with the generalized quantifiers. We are now dealing with some of the generalized quantifiers. We still have to the English resource grammar provide a very large spectrum of different quantifiers, and for now we cluster them into two simple quantifiers and in first order logic, but we want to properly model that in dependent type in the future. So for now, for example, we have this whole set of extension quantifiers that are only translated to an extension, as I said. We also have these three different universal quantifiers that are translated to this implication and universal and implication. And we also have these problems, and even for this simple first step, now we have to deal with this uniqueness, right? So what would be the difference between the book is white and a book is right? So in the quantifier there would potentially be modeled as a existential that only has one element. For now, we are not doing that because of the limitations in the reason step, right? That will force the reason to be much more complex. We also have the negation, translation of the negation, translation of the negation, and we have translations of different predicates. So we have negation in the sense of quantifier, but we also have the negation as a predicate. We have two different translations for them. We also have these named predicates in ERG that presents proper names, for example, and then we transform it in equality. We have cardinality, represents a normalization of numbers that in natural language, and we have these card predicates. And we have many other predicates. For many of those predicates, we have an initial transformation, but we already know that we have to dig much more into that. And potentially some of the semantics of these predicates will clearly need some more than just the higher order, first order that we are kind of producing now. Lessons learned is the complexity of simple things like the event variables. Like, for example, if you take a sentence like "Amen is not walking," what would be the proper semantics of that? We learned that we need to go with the negation as close as possible to the event. Otherwise, we have not expected semantics. Take, for example, in consideration also no man is walking. What we want from that, right? Our current interpretation that wants this kind of form. We also have problems where variables are not instantiated, as I said before. For now, we just ignore those variables, but eventually we have to instantiate that variable, find another better approach. Many things to explore yet. So to see how far we got, and if we kind of were able to capture the proper semantics of the sentence, our idea was to make a first exploration about first test and exploration about, okay, what is the semantic, is it useful or not, right? What's the best way to test a library that transforms language into logic, right? So one of the approaches is to use a data set of text entailment, for example. So we suppose that we have a theory, a sentence A that we transform into logic, and sentence B that we transform into logic. We can check if that implication holds, provided some set of axioms. If that is the case, then the sentence A entails sentence B. We can also test for contradictions, checking if from the set of axioms we have a negation of the conjunction of these two formulas. So this is what we did for the SIG data set. For this SIG data set, we constructed by hand 24 axioms that I added incrementally during the test. So axioms like this one that generalize the idea of the fact that the man is a person, and this is a kind of axiom that can be learned later from resources like WordNet. And we also have some axioms that semantically define the ideas of the ERG predicates. So the English resource grammar has abstract predicates like compound that's kind of generalize the idea of how to the nom compounds. What is the semantic of nom compounds? And for dealing with that, we also have axioms over those predicates. But the SIG data set poses a lot of questions that goes far from the logical.
But you have to go as soon as possible to the end of your presentation. Okay.
So entailment is a different task because it's in many of the cases it's not well defined. So I have a few examples where people would think twice about what is exactly, if the label that providing the SIG data sets is right. Thanks for Johan Boss that discussed some more examples about what we have to think about if you have in the different construction here. May require a deep thought about what is really what is the semantic relation between the sentences. But regardless of the difficulty, remember that we are just trying to test our library. And the SIG has 6,000 sentences. We are able to parse almost all of them, 6,000, and only 23 were not able to parse, but 6 is not balanced. So we reduce the SIG to a subset of a balanced data set with 333 sentence pairs for each of the labels, and we are able to obtain these results. So 35 and 40% of accuracy in contradiction and neutrality, we got 100%. Many problems arise from that. We are still working on the tail analysis of these problems. The majority of the problems are related with the ambiguity. So sentences like this has more than 6,000 readings, and the best way to deal with this ambiguity is yet to be discussed. And the next step means the translation from Python to Lima. As I said before, I already have a code to start that. Proper evaluation of parser rank, that is one possibility to deal with the ambiguity. How to learn the axioms automatically is another thing. And finally, going back to the discussion about what is the final logical formula, logical language that we want. As I said, we want to explore the idea of going much beyond high order logic and going to dependent type. So dependent type could eventually solve problems like what will be the proper semantics of this kind of a sentence, right? You don't want to instantiate over individuals something that are not even created. The sentence is saying that's not existed, right? So to avoid the quantification over individual, dependent type introduce other different the idea of predicates are not over individuals but over types, right? I'm not have time to explore that, but just put here the ideas. Thank you, and sorry for having to be so quickly.